All right, let's look at this stacked blocks problem. I like this problem because it really can give you a feeling for normal forces and forces in between objects that are in contact. This is an important application to be able to understand, and this problem kind of goes right to the heart of that. So we have three blocks, they're stacked up, and they are in an elevator, and the elevator is accelerating upward at A prime. So I'm just going to put that in our diagram. Our brains like pictures. So this whole enchilada here is accelerating upward at A prime, and that acceleration is given. Block masses are given as shown, 3, 2, and 1m. And the normal, what we're asked to determine is the normal forces between the blocks. So we're being asked to determine the forces that are at these interfaces here. Notice it's between the blocks. So between blocks 2m and 3m, and between blocks M and 2M. At those surfaces where, at those interfaces where the surfaces come together, there are normal forces, and we're being asked to find what those are. So in order to do this, as usual, this is a force analysis problem. So we want free body diagrams here. I'm going to go ahead and say upward is positive. My acceleration direction I know is upward. That's given to me clearly in this problem. So I'm going to set upward to be positive for everything I do here. And then I'll go ahead and start free body diagrams. So when you're looking at force analysis problems, free body diagrams, force identification and free body diagrams, those are always what you do first. Always what you do first. I don't want to see you launching into algebra or doing some other analysis before you get your free body diagrams because you don't know that you have your force analysis done correctly. So we'll start here, the free body diagram for block M. We always label our free body diagrams so that when someone looks at our paper, they can see what it is that we're working on. I'll do M. I'm just going to lay these out first. Free body diagram for 2M, and then of course for my 3M block. And in all those cases, I've got upward positive. Great. Okay, so I'm going to change my color here and just start popping in what my forces are. So fairly simple. If I look at block M, what's in contact with it? Just the surface below it, which is the interface of block 2M there. So that's a normal force being exerted upward on block M. I'll go ahead and put that in as a normal force. Now I need to subscript this in some way. And the way that I subscript normal forces like this is to indicate which interface that normal force is related to. So this normal force is the normal force between block M and 2M. So the subscript I'm going to put here is normal force 1, 2 at the interface between blocks 1 and 2 there. And that's the only thing that's touching that block. The only other force on it is our invisible force, which is the weight of that block. So the weight of block M is going to be its mass multiplied by G downward. So that's weight 1 there. And you can put that in as a W for weight. I think in the written solutions I've done that. Or you can, if you're comfortable with that already and you're using language correctly and stuff, you can go ahead and pop in the magnitude of the weight right there. Okay, block 2M. So we look again, what's in contact with the block 2M? Well, it is in contact with block 3M underneath it. So block 3M, that interface at 3M is pushing upwards on block 2M, the normal force. That normal force is the normal force between blocks 2 and 3. So I'm going to subscript that 2 and 3 there. So I just want to make really clear here. This force, this N23, is happening at the interface of 2 and 3, right there. Whereas this force, 1, 2, is happening at the interface of 1 and 2, right there. Okay? So whenever we're using a normal force, we have to be keeping track of exactly which interface that normal force is related to. All right, going back to my forces. So that is taking this, we're looking at the block 2M. Underneath it, there's an upward force, 3M's in contact with it. But the block M is also in contact with block 2M, right? The block above it is also touching it, and it's providing a downward force here. And that downward force is the force at the interface between blocks 1 and 2. So if I were going to highlight this, it would highlight in this orange color here, because the downward force is due to the contact that block 2M has from block M, which is sitting on top of it. Those are the two contact forces that's being contacted in two places, above and below. And then we have, of course, the weight, which is also exerted downward. That's going to be 2 mg in this case, because we know the mass is 2m. And then I'll look at the 3M block. What's touching the 3M block? Well, it has the surface underneath it, the table or the bottom, the floor of the elevator, I guess, which it's sitting on. And that's exerting an upward force on it. Now, because I don't care about the elevator and we're not like going to analyze the elevator itself, I'm just going to call this normal force N sub 3. I'm not going to call it 3E for 3 in elevator, because my analysis ends at this block, right? I'm only being asked to determine forces in between the blocks here. So I'm just going to subscript that 3, and that helps to also signify that like I'm not going down the ladder anymore. I'm done. And then I ask myself, what else is touching the block? So this N3 is relevant to the normal force that is exerted on the bottom of the 3M block, but there's also a normal force exerted on the top of the 3M block because it's in contact with the 2M block. So that's going to be a downward force on the 3M block, and that force is going to be N23 because it is related to the interface between blocks 2 and 3. So this would be yellow. Here, it's related to the interface between blocks 2 and 3, which I've colored there yellow, just trying to keep track of interfaces, relating to interfaces for you. And then, of course, so those were the two contact forces, above and below. And then, of course, we have weight of block 3 here. So plus 3m, that's its mass, multiplied by g, it's the magnitude of its weight. Okay, so those are all our forces. Now, a common mistake here, a common error when I usually when I view students' work, if I'm doing this in person, I walk around and I look over your shoulders and see what you're doing, is I will see more than one weight listed on a free body diagram, as the student will think, oh, well, the weight of the 2M block is being directed down onto the 3M block. And that is not correct. It's not correct. So if you have that on your paper, stop and go back. And let's fix that now and make sure that that habit doesn't move into the future. On any free body diagram, which is depicted representing any one body, there should ever only be one weight. Remember that weight is the gravitational attraction to the earth. Yeah? That's the relationship between the body and the earth. That's it. Only one. You have one of those. You get one invisible force. Any other force on your free body diagram must be a contact force. Any other force must be a contact force. So no made up forces, no assumed forces, no magic here. And this is nice. Actually, this is good news because it means that you can be really analytical when you look at your free body diagrams and just ask yourself, just know that you get weight, and then any other force has to be caused by contact. So again, if your intuition is telling you something else, let go of that and use your analytical mind. It makes sense that this is new, and often learning is going to feel uncomfortable and a little bit different. So, moving forward, we're going to apply Newton's second law here to each of these cases. To my free body diagram M case, I'm going to apply it. I have upward positive, so that'll give me N12 minus mg equals this body's mass, which is m, multiplied by the acceleration, which is given in this problem as a prime. So here's my Newton's second law expression. So what I'm going to do on this line is simply my Newton's second law expressions, and I call that Newton 2. So for the 2m block, I'm going to do the same thing and I'll render that equation n sub 2, 3 minus n, oh, sorry, that's messy, minus n sub 1, 2 minus 2mg is equal to its mass, 2m, times acceleration, which is given again as a prime. They're all accelerating together in this elevator. And the 3m block, what do I have here? N3 minus N23 minus 3mg, those are both downward directed, so they're negative, is going to be equal to its mass, 3m, times acceleration, a prime. Okay, so I've got three equations. Let me pause and let's ask ourselves about unknowns. So what are my unknowns in this problem? So my masses are known, the acceleration is known. What's unknown are the normal force 1, 2, the normal force 2, 3, and the normal force 3. So three unknowns. I have three equations. So that leads to a smiley face. That's good. We're good to go. So again, proceed algebraically in whatever way makes sense to you. Um, Feel free to look at the written solutions for how I did some algebra there, but you don't need to do the algebra in exactly the same way. Algebra, again, is personal. What we end up with here for our final result is for normal force 1, 2, we get m times quantity g plus a prime. And for normal force 2, 3, 3m times quantity g plus a prime. So that those are our results in both those cases. And notice you might be like, well, why is she not solving for n sub 3? N sub 3 wasn't really asked for in this problem. So for this particular problem, really what we were asked to determine was the normal forces between the blocks. So you could, obviously, you have enough information to solve for n sub 3, but I'm not going to finish that because that wasn't asked for, and I want to try to be precise. So normal force between the blocks, there are three blocks, there are two normal forces, therefore, that are interior to the set of three.